Mir was a space station that operated in low Earth orbit from 1986 to 2001, run by the Soviet Union and later by Russia. Mir was the first modular space station and was assembled in orbit from 1986 to 1996. It had a greater mass than any previous spacecraft. At the time it was the largest artificial satellite in orbit, succeeded by the International Space Station after Mir's orbit decayed. The station served as a microgravity research laboratory in which crews conducted experiments in biology, human biology, physics, astronomy, meteorology and spacecraft systems with the goal of developing technologies required for permanent occupation of space. Mir was the first continuously inhabited long-term research station in orbit and held the record for the longest continuous human presence in space, at 3,644 days, until it was surpassed by the ISS on the 23rd of October 2010. It holds the record for the longest single human spaceflight, with Valery Polyakov spending 437 days and 18 hours on the station between 1994 and 1995. Mir was occupied for a total of 12.5 years, out of its 15-year lifespan, having the capacity to support a resident crew of 3 or larger crews for short visits. Following the success of the Salyut program, Mir represented the next stage in the Soviet Union's space station program. The first module of the station, known as the core modular base block, was launched in 1986 and followed by 6 further modules. Proton rockets were used to launch all of its components except for the docking module, which was installed by Space Shuttle mission SDS-74 in 1995. When complete, the station consisted of 7 pressurized modules and several unpressurized components. Power was provided by several photovoltaic arrays attached directly to the modules. The station was maintained at an orbit between 296 kilometers and 421 kilometers altitude and traveled at an average speed of 27,700 kilometers per hour, completing 15.7 orbits per day. The station was launched as part of the Soviet Union's manned spaceflight program effort to maintain a long-term research outpost in space, and following the collapse of the USSR, was operated by the new Russian Federal Space Agency. As a result, most of the station occupants were Soviet. However, through international collaborations such as the Intercosmos, Russia.Mir and Shuttle.Mir programs, the station was made accessible to space travelers from several Asian, European and North American nations. Mir was deorbited in March 2001 after funding was cut off. The cost of the Mir program was estimated by former RKA General Director Yuri Koptev in 2001 as $4.2 billion over its lifetime. Origins. Mir was authorized on the 17th of February 1976 decree to design an improved model of the Salyut DOS-17K space stations. 4 Salyut space stations had been launched since 1971, with 3 more being launched during Mir's development. It was planned that the station's core module would be equipped with a total of 4 docking ports, 2 at either end of the station as with the Salyut stations, and an additional 2 ports on either side of a docking sphere at the front of the station to enable further modules to expand the station's capabilities. By August 1978, this had evolved to the final configuration of 1 aft port and 5 ports in a spherical compartment at the forward end of the station. It was originally planned that the ports would connect to 7.5-TONNE modules derived from the Soyuz spacecraft. These modules would have used a Soyuz propulsion module, as in Soyuz and Progress, and the descent and orbital modules would have been replaced with a long laboratory module. However, following a February 1979 governmental resolution, the program was consolidated with Vladimir Shelemov's manned Almaz military space station program. The docking ports were reinforced to accommodate 20-ton space station modules based on the TKS spacecraft. NPO Energia was responsible for the overall space station, with work subcontracted to KB Salyut. Due to ongoing work on the Energia rocket and Salyut 7, Soyuz-T, and Progress spacecraft, KB Salyut began work in 1979, and drawings were released in 1982 and 1983. New systems incorporated into the station included the Salyut 5B digital flight control computer and gyrodyne flywheels, Ker's automatic rendezvous system, Luch satellite communications system, electron-oxygen generators, and Vosdok carbon dioxide scrubbers. By early 1984, work on Mir had halted while all resources were being put into the Buran program in order to prepare the Buran spacecraft for flight testing. Funding resumed in early 1984 when Valentin Glashko was ordered by the Central Committee's Secretary for Space and Defense to orbit in Mir by early 1986, in time for the 27th Communist Party Congress. It was clear that the planned processing flow could not be followed and still meet the 1986 launch date. It was decided on Cosmonauts Day 1985 to ship the flight model of the base block to the Baikonur Cosmodrome and conduct the systems testing and integration there. The module arrived at the launch site on the 6th of May, with 1,100 of 2,500 cables requiring rework based on the results of tests to the ground test model at Khrunichev. In October, the base block was rolled outside its cleanroom to carry out communications tests. The first launch attempt on the 16th of February 1986 was scrubbed when the spacecraft communications failed, but the second launch attempt, on the 19th of February 1986 at 21 hours 28 minutes and 23 seconds UTC, was successful, meeting the political deadline. Station structure. Assembly. The orbital assembly of Mir began on February 19, 1986 with the launch of the Proton K rocket. 4 of the 6 modules which were later added followed the same sequence to be added to the main Mir complex. Firstly, the module would be launched independently on its own Proton K and chase the station automatically. It would then dock to the forward docking port on the core module's docking node, then extend its fly-upper arm to mate with a fixture on the node's exterior. The arm would then lift the module away from the forward docking port and rotate it onto the radial port where it was to mate, before lowering it to dock. The node was equipped with only 2 Konus drogues, however, which were required for dockings. This meant that, prior to the arrival of each new module, the node would have to be depressurized to allow spacewalking cosmonauts to manually relocate the drogue to the next port to be occupied. The other 2 expansion modules, KVANT-1 in 1987 and the docking module in 1995, followed different procedures. KVANT-1, having, unlike the 4 modules mentioned above, no engines of its own, was launched attached to a tug based on the TKS spacecraft, which delivered the module to the aft end of the core module instead of the docking node. Once hard docking had been achieved, the tug undocked and deorbited itself. The docking module, meanwhile, was launched aboard Space Shuttle Atlantis during SDS-74 and mated to the orbiter's orbiter docking system. Atlantis then docked, via the module, to Crystal, then left the module behind when it undocked later in the mission. Various other external components, including 3 truss structures, several Several experiments and other unpressurized elements were also mounted to the exterior of the station by cosmonauts conducting a total of 80 spacewalks over the course of the station's history. The station's assembly marked the beginning of the third generation of space station design, being the first to consist of more than one primary spacecraft. First-generation stations such as Salyut 1 and Skylab had monolithic designs, consisting of one module with no resupply capability, whilst the second-generation stations Salyut 6 and Salyut 7 comprised a monolithic station with two ports to allow consumables to be replenished by cargo spacecraft such as Progress. The capability of Mir to be expanded with add-on modules meant that each could be designed with a specific purpose in mind, thus eliminating the need to install all the station's equipment in one module. Pressurized modules. In its completed configuration, the space station consisted of 7 different modules, each launched into orbit separately over a period of 10 years by either Proton K rockets or Space Shuttle Atlantis. Unpressurized elements. In addition to the pressurized modules, Mir featured several external components. The largest component was the Sophora girder, a large scaffolding-like structure consisting of 20 segments which, when assembled, projected 14 meters from its mount on KVANT-1. A self-contained thruster block, the VDU, was mounted on the end of Sophora and was used to augment the roll control thrusters on the core module. The VDU's increased distance from Mir's axis allowed an 85% decrease in fuel consumption, reducing the amount of propellant required to orient the station. A second girder, Rapana, was mounted aft of Sophora on KVANT-1. This girder, a small prototype of a structure intended to be used on Mir 2 to hold large parabolic dishes away from the main station structure, was 5 meters long and used as a mounting point for externally mounted exposure experiments, to assist in moving objects around the exterior of the station during EVAS. Mir featured 2 Strahler cargo cranes mounted to the sides of the core module, used for moving spacewalking cosmonauts and parts. The cranes consisted of telescopic poles assembled in sections which measured around 1.8 meters when collapsed, but when extended using a hand crank were 14 meters long, meaning that all of the station's modules could easily be accessed during spacewalks. Each module was fitted with a number of external components specific to the experiments that were carried out within that module, the most obvious being the Travers antenna mounted to Prida. This synthetic aperture radar consisted of a large dish-like framework mounted outside the module, with associated equipment within, used for Earth observations experiments, as was most of the other equipment on Prida, including various radiometers and scan platforms. KVANT-2 also featured a number of scan platforms and was fitted with a mounting bracket to which the Cosmonaut Maneuvering Unit, or ICAR, was mated. This backpack was designed to assist cosmonauts in moving around the station and the planned burn in a manner similar to the U.S. Manned Maneuvering Unit, but it was only used once, during EO5. In addition to module-specific equipment, KVANT-2, Crystal, SPEKTR and Prida were each equipped with one LIAPA arm, a robotic arm which, after the module had docked at the core module's forward port, grappled one of 2 fixtures positioned on the core module's docking node. The arriving module's docking probe was then retracted, and the arm raised the module so that it could be pivoted 90 degrees for docking to one of the 4 radial docking ports. Power supply. Photovoltaic arrays powered Mir. The station used a 28-volt DC supply which provided 5, 10, 20 and 50 amp taps. When the station was illuminated by sunlight, several solar arrays mounted on the pressurized modules provided power to Mir's systems and charged the nickel-cadmium storage batteries installed throughout the station. The arrays rotated in only 1 degree of freedom over a 180 degrees arc, and tracked the sun using sun sensors and motors installed in the array mounts. The station itself also had to be oriented to ensure optimum illumination of the arrays. When the station's all-sky sensor detected that Mir had entered Earth's shadow, the arrays were rotated to the optimum angle predicted for requiring the sun once the station passed out of the shadow. The batteries, each of 60 Ah capacity, were then used to power the station until the arrays recovered the maximum output on the day side of Earth. The solar arrays themselves were launched and installed over a period of 11 years, more slowly than originally planned, with the station continually suffering from a shortage of power as a result. The first 2 arrays, each 38 square meters in area, were launched on the core module, and together provided a total of 9 kilowatts of power. A third dorsal panel was launched on KVANT-1 and mounted on the core module in 1987, providing a further 2 kilowatts from a 22 square meters area. KVANT-2, launched in 1989, provided 2 10-meters-long panels which supplied 3.5 kilowatts each, whilst Crystal was launched with 2 collapsible, 15-meters-long arrays which were intended to be moved to KVANT-1 and installed on mounts which were attached during a spacewalk by the EO-8 crew in 1991. This relocation was not begun, however, until 1995, when the panels were retracted and the left panel installed on KVANT-1. By this time all the arrays had degraded and were supplying much less power. To rectify this, spacecraft, which had initially been designed to carry 2 arrays, was modified to hold 4, providing a total of 126 square meters of array with 16 kilowatts supply. 2 further arrays were flown to the station on board the Space Shuttle Atlantis during SDS-74, carried on the docking module. The first of these, the Mir Cooperative Solar Array, consisted of American photovoltaic cells mounted on a Russian frame. It was installed on the unoccupied mount on KVANT-1 in May 1996 and was connected to the socket that had previously been occupied by the core module's dorsal panel, which was by this point barely supplying 1 kilowatt. The other panel, originally intended to be launched on Prida, replaced the crystal panel on KVANT-1 in November 1997, completing the station's electrical system. Total power supply by solar arrays, had the older ones not been degraded, would have been 42 kilowatts by 1997. Orbit control Mir was maintained in a near-circular orbit with an average perigee of 354 kilometers and an average apogee of 374 kilometers, traveling at an average speed of 27,700 kilometers per hour and completing 15.7 orbits per day. As the station constantly lost altitude because of a slight atmospheric drag, it needed to be boosted to a higher altitude several times each year. This boost was generally performed by Progress resupply vessels, although during the Shuttle-Mir program the task was performed by U.S. space shuttles, and, prior to the arrival of KVANT-1, the engines on the core module could also accomplish the task. The attitude of the station was independently determined by a set of externally mounted sun, star and horizon and senses. Attitude information was conveyed between updates by rate sensors. Attitude control was maintained by a combination of two mechanisms in order to hold a set attitude. A system of 12 control moment gyroscopes rotating at 10,000 revolutions per minute kept the station oriented. 6 CMGs being located in each of the KVANT1 and KVANT2 modules. When the attitude of the station needed to be changed, the gyrodynes were disengaged. Thrusters were used to attain the new attitude and the CMGs were re-engaged. This was done fairly regularly depending on experimental needs. For instance, Earth or astronomical observations required that the instrument recording images be continuously aimed at the target, and so the station was oriented to make this possible. Conversely, materials processing experiments required the minimization of movement on board the station, and so Mir would be oriented in a gravity gradient attitude for stability. Prior to the arrival of the modules containing these gyrodynes, the station's attitude was controlled using thrusters located on the core module alone, and, in an emergency, the thrusters on docked Soyuz spacecraft could be used to maintain the station's orientation. Communications. Radio communications provided telemetry and scientific data links between Mir and the RKA Mission Control Center. Radio links were also used during rendezvous and docking procedures and for audio and video communication between crew members, flight controllers and family members. As a result, Mir was equipped with a number of communication systems used for different purposes. The station communicated directly with the ground via the Lyra antenna mounted to the core module. The Lyra antenna also had the capability to use the Luch data relay satellite system and the network of Soviet tracking ships deployed in various locations around the world. UHF radio was used by cosmonauts conducting EVAS. UHF was also employed by other spacecraft that docked to or undocked from the station, such as Soyuz, Progress, and the Space Shuttle, in order to receive commands from the TSUP and Mir crew members via the Toru system. Microgravity. At Mir's orbital altitude, the force of Earth's gravity was 88% of sea-level gravity, while the constant free fall of the station offered a perceived sensation of weightlessness. The onboard environment was not one of weightlessness, zero gravity. The environment was, however, often described as microgravity. This state of perceived weightlessness was not perfect, however, being disturbed by 5 separate effects: the drag resulting from the residual atmosphere, vibratory acceleration caused by mechanical systems and the crew on the station, orbital corrections by the onboard gyroscopes or thrusters, tidal forces. Any parts of Mir not at exactly the same distance from Earth tended to follow separate orbits. However, as each point was physically part of the station, this was impossible, and so each component was subject to small accelerations from tidal forces. The differences in orbital plane between different locations on the station. Life support. Mir's environmental control and life support system provided a controlled atmospheric pressure, fire detection, oxygen levels, waste management and water supply. The highest priority for the ECLSS was the station's atmosphere, but the system also collected, processed, and stored waste and water produced and used by the crew, a process that recycles fluid from the sink, toilet, and condensation from the air. The electron system generated oxygen, bottled oxygen and solid fuel oxygen generation canisters. A system known as VICA provided backup. Carbon dioxide was removed from the air by the Vozdug system. Other byproducts of human metabolism, such as methane from the intestines and ammonia from sweat, were removed by activated charcoal filters. Similar systems are presently used on the International Space Station. The atmosphere on Mir was similar to Earth's. Normal air pressure on the station was 101.3 kilopascals, the same as its sea level on Earth. An Earth-like atmosphere offers benefits for crew comfort, and is much safer than the alternative, a pure oxygen atmosphere, because of increased fire risks such as occurred with Apollo 1. International cooperation. Intercosmos was a Soviet Union space exploration program which allowed members from the military forces of Allied Warsaw Pact countries to participate in manned and unmanned space exploration missions. Participation was also made available to governments of countries such as France and India. Only the last 3 of the program's 14 missions consisted of an expedition to Mir, but none resulted in an extended stay in the station. Mohammad Faris, EP1 Syria, Alexander Panayotov Alexandrov, EP2 Bulgaria, Abdul Ahad Momond, EP3 Afghanistan. European involvement. Various European astronauts visited Mir as part of several cooperative programs: Jean-Luc Crétin, Arrogats, France; Helen Sharman, Project Juno, UK; Franz Veerbock, Russia.Mir, 91, Austria; Klaus-Dietrich Flade, Mir, 92, Germany; Michel Tognini, Antares, France; Jean-Pierre Hainer, Altair, France; Ulf Merbold, Russia.Mir, 94, Germany; Thomas Reiter, Russia.Mir, 95, Germany; Claude Hainer, Cassiopeia, France; Reinhold Ewald, Mir, 97, Germany; Leopold Ihartz, Pegasus, France; Ivan Bülow, Stefanik, Slovakia. Shuttle-Mir program. In the early 1980s, NASA planned to launch a modular space station called Freedom as a counterpart to Mir, while the Soviets were planning to construct in Mir 2 in the 1990s as a replacement for the station. Because of budget and design constraints, Freedom never progressed past mock-ups and minor component tests, and, with the fall of the Soviet Union and the end of the space race, the project was nearly cancelled entirely by the United States House of Representatives. The post-Soviet economic chaos in Russia also led to the cancellation of Mir 2, though only after its base block, decayed, had been constructed. Similar budgetary difficulties were faced by other nations with space station projects, which prompted the U.S. government to negotiate with the European states, Russia, Japan, and Canada in the early 1990s to begin a collaborative project. In June 1992, American President George H.W. Bush and Russian President Boris Yeltsin agreed to cooperate on space exploration. The resulting agreement between the United States of America and the Russian Federation concerning cooperation in the exploration and use of outer space for peaceful purposes called for a short joint space program with one American astronaut deployed to the Russian space station Mir and 2 Russian cosmonauts deployed to a space shuttle. In September 1993, U.S. Vice President Al Gore, Jr., and Russian Prime Minister Viktor Chernomyrdin announced plans for a new space station, which eventually became the International Space Station. They also agreed, in preparation of this new project, that the United States would be heavily involved in the Mir program as part of an international project known as the Shuttle-Mir program. The project, sometimes called Phase 1, was intended to allow the United States to learn from Russian experience in long-duration spaceflight and to foster a spirit of cooperation between the two nations and the space agencies, the U.S. National Aeronautics and Space Administration and the Russian Federal Space Agency. The project prepared the way for further cooperative space ventures, specifically Phase 2 of the joint project, the construction of the International Space Station. The program was announced in 1993, the first mission started in 1994, and the project continued until its scheduled completion in 1998. 11 Space Shuttle missions, a joint Soyuz flight, and almost 1,000 cumulative days in space for U.S. astronauts occurred over the course of 7 long-duration expeditions. Other visitors: Toyohiro Akiyama, Cosmoreporter Japan. A British con artist, Peter Rodney Llewellyn, almost visited Mir in 1999 on a private contract after promising $100 million for the privilege.